Hello, everyone. This is our third lecture on the structure of Ricci shrinkers. So first of all, let's recall a Ricci shrinker is a triple of Riemannian manifold coupled with a potential function f satisfy the following equation. So this is a Ricci shrinker. That means the Ricci curvature plus the Hessian f is equal to G over half. Here, we will denote the left-hand side by Ricci f, that is the Bakery-Emery Ricci tensor. Last time, we have shown some estimate for the potential function. In particular, it implies that for any Ricci shrinker, the potential function f has a minimal point. So we will always choose a point P, which is a minimal point. Here, P is a minimal point of our potential function f. So this is taken as a base point. Moreover, last time we have chosen a normalization for our potential function f so that the gradient f squared plus the scalar curvature is equal to the potential function f. So it in particular implies that the f is non-negative because the scalar curvature is always non-negative. And we have other identities like the Laplacian f plus r is equal to n over 2, which is just by taking trace of the original identities in the definition of Ricci shrinkers. Now, in today's lecture, I will introduce an important geometric quantity that is called the Parabolic entropy. The Parabolic entropy was originally introduced by Parabolic for compact Ricci flow. We will see today how that is closely related to the entropy defined on a Ricci shrinker. Now, with all those preparations and normalization, we can define our entropy as a quantity of mu, which is defined as the log integral of e to the negative f over 4 pi to the power n over 2 dv. So that means e to the mu is equal to the integral in the bracket. Now, for any Ricci shrinker, we can define such a quantity that is called the entropy. Now, for instance, if our Ricci shrinker is a trivial one, that is a standard Euclidean with a standard d squared over 4 as potential function, we can easily see that the integral in the bracket is just the Gaussian integral. That is our heat kernel, which is equal to 1, so the mu must be equal to 0. So the entropy of the standard Euclidean space is always equal to 0. Now, by this definition, we can immediately derive some basic estimate for this entropy mu. That is, by the definition, we know that e to the mu is the integral of e to the f over 4 pi to the power n over 2. So this must be greater or equal to the integral restrict on a unit ball around P, right? Now, since the potential function f has the lower bound and upper bound on this unit ball, and whose bound only depends on the dimensional constant, so we can show that all the functions we integrated has a positive lower bound. So this is in particular greater or equal to a positive constant Cn times the volume for the unit ball around the base point P. So that implies that the entropy is closely related to the volume of BP1. Now here we only derived the lower bound, that is give a one directional relationship between those two. Later we'll say that actually e to the mu is comparable to the volume of BP1. Now, how can we understand the entropy defined in this way and how to relate it to the entropy introduced by Parabolic in compact manifold. First of all, we recall by this definition of mu, we can define a probability measure. So now we can define a measure dm, which is e to the negative f minus mu over 4 pi to the power n over 2 dv. So of course, this is a probability measure. Moreover, by closely examining the definition, we can see this is almost equal to the weighted measure we introduced last time. The only difference is we have a constant. So in particular, we know that the weighted Laplacian is also self-adjoint with respect to this new measure dm. Okay. Now, with this given probability measure, in order to derive some interesting relationship between the entropy defined here with the Parabolic entropy, we need to recall the following theorem by Ricci and Embry. So this is called the Ricci-Embry theorem. Now, what does it tell us? So it says that if we have a smooth metric measure space, so here I assume that the measure is defined by our probability measure, satisfy the following condition. If this measure space satisfies, the Ricci f is greater or equal to g over 2. So actually, in our case, this is equal to g over 2. But here I slightly use a slightly stronger condition, or sorry, a slightly weaker condition. That is, Ricci f is greater or equal to g over 2. Then for any rho such that the square root of rho is a smooth function with compact support, and the integral of rho with respect to dm is equal to 1, then we have the following inequality. That is, the integral of rho log rho with respect to dm is less or equal to integral of gradient rho squared over rho dm. So this is the classic Ricci-Embry inequality, which was originally proved in early 80s for compact manifold, and later it was generalized to any complete Riemannian manifold as long as it satisfies the inequality for Ricci-Embry ridge tensor. Now, by using the Ricci-Embry theorem, we can relate our entropy with Paramans' celebrated entropy. So before we do that, I will first of all write down the definition for Paramans entropy. So let's see, Paramans entropy. Now, Paramans entropy is defined actually for any complete Riemannian manifold with a scaling factor tau, which is positive. It defines as a W entropy, which depends on the metric G, some function U, and the scaling factor tau as the following integral. That is the tau for gradient U squared plus scalar curvature U squared minus U squared log U squared dV. So V is the volume form with respect to the metric G, the minus some normalization constant, n plus n over 2 times log 4 pi tau. So this is Paramet's definition for the W entropy, and for his definition of mu entropy, we just need to take infimum for all such U as long as its squared has the integral 1. So the mu entropy, mu g tau, is we take all infimum for W g u tau, where U satisfies the squared has the integral 1 and U is C0 infinity. Now notice that for any complete Riemannian manifold, it's possible that the mu entropy can reach negative infinity. Now the reason why we compare the entropy of the Ricci shrinker to the entropy to Paramet's entropy is because we try to use some nice property for Paramet's entropy, like the no local collapsing theorem, which we will talk about later, and like the monotonicity for Paramet's entropy. Okay, now we can state the comparison between those two similar different entropies. So this is proved by Carrier and Lee. So it states that if MNGF is a Ricci shrinker, then the Paramet's entropy mu g1, so that is when the scaling factor tau is equal to 1, is equal to the entropy mu. So here, the right-hand side, this quantity is the entropy defined at the beginning of this lecture. That is the entropy defined on Ricci shrinker. Moreover, the minimizer for mu g1 is taken for a special function, that is wg e to the negative f0 over 2, 1. Here, the function f0 is defined by the potential function f plus mu, then plus n over 2 times log 4 pi. So equivalently speaking, this means the e to the negative f0 times dv is equal to our probability measure df. So that means the entropy of Ricci shrinker is equal to the Paramet's entropy at the scale 1. Now let's quickly prove this. So the proof for this fact mainly use the Becquerel-Emery inequality. So first of all, we will show one direction. So one direction. So here I directly choose the test function u to be our e to the negative f0 over 2. So here, of course, we have u squared has the integral 1. So this is by the definition of f0. Now we compute the W entropy by this choice of u, that is WGU1 is just the WG e to the negative f0 over 2, 1. Now by using the definition of the W functional, so that is, I wrote it here. So with some long calculation, so you just choose u to be e to the negative f0 over 2. Then after some calculation, we can rewrite this as the integral of gradient f squared plus scalar curvature plus f minus n times e to the negative f0 dv plus our entropy mu. Now we can use some identity which was derived last time. Now notice that here the gradient f squared plus r is just equal to f. So what we have here is the integral of 2f minus n. So that is e to the negative f0 dv plus mu. Now recall another identity we derived as Laplacian f. X on f is equal to n over 2 minus f. So here, what we integrate here would be negative 2 integral of Laplacian f on f e to the negative f0 dv plus mu. Notice that the Laplacian f is self-adjoint with respect to this measure. So the first integral actually vanishes. So only the second constant mu is left. So this is exactly equal to mu. Okay. So that means with this particular choice of test function u, we show that WGU1 is actually equal to u. Now, if we take all infimum, we have one direction, so that we will obtain the mu G1 is less or equal to the mu divided on the entropy, divided on the Ricci shrinker. So this is one direction. Now we try to prove the other direction, that is mu G1 should be greater or equal to mu as well. For this step, we need to use the Baker-Emery inequality. So other direction. Okay, now how can we use the Baker-Emery inequality? Now for any u, which is smooth with compact support, with the integral of u squared with dv is equal to 1, we can define the following test function rho as u squared times e to the f0. Notice that this choice of rho means the integral of rho squared, so the integral of rho with respect to the probability measure dm should be equal to 1. Now we try to use this rho as the test function in the Baker-Emery theorem. Recall that it says that rho times log rho dm is less or equal to gradient rho squared over rho dm. So this is the Baker-Emery theorem. Now, by our particular choice of rho, we can rewrite this inequality in terms of u and f. So just expand both sides. So here I omit some calculations. Now the left-hand side with this choice of rho can be rewritten as the integral of u squared log u squared, then plus the integral, write down the measure, dv, plus the integral of f0 u squared dv. And the right-hand side, if you use the definition of rho, can be rewritten as 4 times gradient u squared plus gradient f0 squared u squared plus 2 times gradient u squared gradient f0s, then we integrate that with respect to dv. Okay, now by our definition of f0, so recall that f0, the definition above, is equal to f plus mu plus n over 2 times log 4 pi. So I'll circle this. Then we can replace f0 with the f plus some constant. So here, the left-hand side can be rewritten as integral u squared log u squared plus mu plus n over 2 log 4 pi. So this is the left-hand side. And for the right-hand side, we can use the definition for f0. And for the last term, we use the integration by part. So this is the integral 4 gradient u squared plus u squared gradient f squared minus 2 Laplacian f minus f, then dv. Now the expression in the bracket can be rewritten as the scalar curvature minus f. Here we simply use our identities again. Now, since the integral of u squared is equal to 1, by moving the last term to the left-hand side and the first term on the left-hand side to the right-hand side, we obtain the inequality we need. That is mu plus n over 2 log 4 pi is less or equal to integral 4 gradient u squared plus r u squared minus u squared log u squared d. Okay. Now here, by moving those two terms to the right-hand side, we get mu is less or equal to w gu1. So here, this is true for any compactly supported function u as long as its squared has the integral 1. So by taking the infimum, we obtained mu is less or equal to mu g1 by taking the infimum. Okay. So in this way, we have obtained the other direction. So mu is less or equal to mu g1, and for the first part, we have proved that mu is greater or equal to mu g1. Combine those two, we have the identity we want. That is mu g1 is equal to mu. So this important identity has related the entropy defined on Ricci shrinker to Parabolic entropy. Now, actually, we can prove a little bit more. That is, since we know that for Parabolic entropy, it has some monotonicity, and at the same time, we can regard any Ricci shrinker as a self-similar solution to the Ricci flow. So maybe we can relate those two to prove a stronger identity. Now, in order to achieve this, we first of all recall Theorem's monotonicity formula. Now, the monotonicity formula says that assume we have a compact Ricci flow, which exists for at least for a short time. So this is a compact Ricci flow. Then Parabolic shows that for any scaling factor tau, the entropy mu gt tau minus t is always increasing for any t less than the minimum of capital T and tau. So here the t must be less than tau because we try to make the scaling factor tau minus t to be positive. So that means up to some scaling, the mu gt is always increasing along the Ricci flow. Now, I will not give a proof for this fact, but I only want to give some idea how Parabolic proved this. So basically, to prove the monotonicity, we fixed two time t1 and t2. Let's say this is the t1 and t2 is the later time. So I will assume that both t1 and t2 are less than the minimum of capital T and tau. Now, in order to compare the entropy defined at those two times, we first of all choose any test function. Let's say at this later time t2, we choose a function omega bar, which is the test function for the W entropy. Now we solve the conjugate heat equation starting from the omega bar. Then we obtain a function omega t. So actually this omega t also depends on the spatial point. So here omega t is the solution of the conjugate heat equation along the Ricci flow starting with the given function omega bar. So that means omega t is the solution in between T1 and T2. So basically with this choice, we just need to compute the W function at omega t, that is W g T1 omega T1 as a test function with the scaling factor tau minus T1 is less or equal to W GT2 omega T2 and the tau minus T2. So as long as we can show this, then by the any choice for the omega bar, then we can prove the monotonicity for the mu function. However, to derive the last inequality, it involves a lot of computations and integration by parts. So this is the key inequality. So actually, Pyramid has derived a very strong inequality when you choose the test function as a solution for the conjugate heat equation. Okay, I will not go into details for this. We just need to know that for compact Ricci flow, the entropy is increasing along the flow. Now, if we try to generalize this monotonicity for any Ricci flow, for instance, on a Ricci flow on a manifold with maybe on non-compact manifold, we immediately run into some problems. One reason for this is we do not have a heat kernel for general non-compact Ricci flow. So the heat kernel might not exist because the curvature at spatial infinity might be very large. The second obstacle for this generalization is we might not use the integration by parts. So here I write down some difficulties if we try to generalize this. The first one is the existence for the heat kernel. Second of all is we cannot use the integration by parts. So both are actually easily derived when you restrict ourselves our compact manifold, but this is not available for general non-compact Ricci flow. Now, luckily, if we restrict ourselves on the Ricci flow associated with a Ricci shrinker, this is actually true. We can overcome those difficulties by choosing a family of color functions. Now, let me state a theorem proved by myself and Wang. Now, this says that if the MNGF is a Ricci shrinker, recall that we have associated Ricci flow solution, which is a self-similar Asian solution. Then the entropy mu GT tau minus T is increasing as long as the T is less than the minimum of tau and 1. So here, the maximal defining time for the Ricci flow is equal to 1, so it must be less than 1. So that means if we only restrict ourselves on self-similar solutions to the Ricci flow, That is, in the case of Ricci shrinker, the monotonicity of Theorem still holds. Now, I will not give details for this proof. I just want to show how we overcome the difficulties I mentioned before. That is how we construct a heat kernel and integration by parts. Now, both can be achieved by constructing a nice family of cutoff functions. Then we can transform the problems of non-compact manifold to compact manifold. So the key point here is to construct a family of cutoff functions. So notice that for general non-compact Riemannian manifold, the existence of cutoff functions might be hard to get. For instance, only if we assume some curvature condition like the Ricci curvature is non-negative can we construct some cutoff functions. But for Ricci shrinkers, the existence for the cutoff function is actually already made. It can be directly chosen as the cutoff function related to our potential function. So the reason is we have shown in the first lecture that the potential function f is almost equal to d squared over 4. That means we can use the potential function as a replacement for the distance function. So when we construct a cutoff function, we can just use the potential f to do that. Now here, recall that for Ricci shrinker, we have a family of diffeomorphism so that the flow gt is divided by 1 minus t psi t star g. So this is the Ricci flow divided with respect to the Ricci shrinker. Now we can also define a potential function at the time t as the pullback of our original potential function f. Okay. Now at the time t, actually the gt and ft also satisfy the equation for Ricci shrinker, but possibly with a different scaling. So in fact, one can easily check the Ricci curvature of gt plus the Hessian of ft is equal to gt over 2 times 1 minus t. So here, the Hessian curvature is with respect to the metric gt. So basically, they are exactly the same Ricci shrinker, but with a different scaling and diffeomorphism. Now, as one can prove, like in the first lecture, we can obtain the estimate for the potential function ft as well. So one can show the potential function 1 minus t times ft is almost equal to the distance function of gt squared with respect to the base point p over 4. So that means 1 minus t times ft is almost the same as the d squared over 4. So it gives us another replacements for the distance function, but at a possible different time t. Okay, now with those choices, we can define a cutoff function. Now we define our cutoff function phi r as the eta of 4 1 minus t ft over r squared, where eta is a standard cutoff function, so that when x is less or equal to 1, it's equal to the constant 1, and when x is greater or equal to 2, it's equal to 0. So that is a standard cutoff function from 1 to 0. So this is the choice for eta. Now, since we have replaced the we have composed the eta with the expression inside. You can see the inside expression is nothing but the d squared over r squared. So this can be chosen as a nice cutoff function for our Ricci flow associated with a Ricci shrinker. In particular, for this choice, we have the following parabolic estimate and gradient estimate. First of all, we know that the gradient phi r is always equal to c times r to the inverse. Moreover, if we consider the heat operator on phi r, we have partial t minus Laplacian phi r is always bounded by c times r to the negative 2. Here, the constancy only depends on the dimension. Okay? So this is actually a nice thing. As long as we have those two estimates for the first order and the second order for phi r, then we can basically do anything we have done like we did in the compact Ricci flow. For instance, we can use those cutoff function to prove the existence for the heat kernel. Moreover, we can use that to perform the integration by parts. Anyway, by carefully add the cutoff function in each step in Parabolic proof, we can prove that the monotonicity formula is also true on the Asian solution associated to a Ricci shrinker. Okay. Now, with this property, we can show a stronger identity between the Parabolic entropy and the entropy of Ricci shrinkers. Now, with that, we can prove that if MNGF is a Ricci shrinker, we can show that the entropy mu g tau is decreasing for tau in between 0 and 1, and increasing for tau greater or equal to 1. So I can draw a graph for this. So this is the value for mu g tau, and this is the value for tau. You can see as tau increases, first of all, the value for mu g tau is decreasing until it approaches 1, then it might be increasing. So this is the picture for the mu g tau on the Ricci shrinker. Now, one particular consequence for this picture is we can show that the mu g1 is the minimal point for mu g tau. So in particular, we show that the infimum for all positive tau of mu g tau is actually equal to mu g1, which is equal to the entropy on the Ricci shrinker. Right? So the last identity is the so-called strong relation between the Parabolic entropy and the entropy on the Ricci shrinker. Now, how can we prove the fact I mentioned, that is the mu g tau is first decreasing and then increasing? So to prove this, we just need to use the self-similar property for Ricci shrinkers. So recall that the gt is 1 minus t psi t star g Now, since we know that mu gt tau minus t is increasing, so as long as it's defined, that means if we replace gt with 1 minus t psi t star g, this is mu 1 minus t psi t star g tau minus t is also increasing. Now, by the scaling invariant property for the mu entropy, we can rewrite this as mu psi t star g tau minus t over 1 minus t. And since the entropy is the same with different diffeomorphism, so the last one is mu g tau minus t over 1 minus t. Okay. So this means for any tau, as long as t is less than the minimum of 1 n tau, the last quantity, the mu g tau minus t over 1 minus t is always increasing. So one can show by a different choice of tau, it's easy to see. Now, by different choices of tau, one can show the mu g tau is decreasing if tau is less than 1 and increasing if tau is greater than 1. So this is the choice for, so when you choose the different choice for tau in this identity, so let me circle that. We know that since this is increasing, then we can show that the mu g tau is decreasing when tau is less than 1 and increasing when tau is greater than 1. Now, the situation at the point when tau is equal to 1 is a little bit more involved. So here I will not go into details for this. That involves some careful analysis around the point when tau is near 1. So actually, this is also true when tau is less or equal to 1, and true when tau is greater or equal to 1. So by doing some further analysis when tau is equal to 1. Now I want to make another remark. That is, not only we can show that the function has the given monotonicity, but also we can show mu g tau is actually a continuous function. So this is a continuous function with respect to the argument tau. Okay, now what is the importance for this theorem? That is, what can we obtain if we already know that the entropy for any scale, that is mu g tau for any tau, is always greater or equal to our entropy mu. So first of all, it gives us the strong Sobolev inequality, strong log Sobolev inequality. The second consequence is we can use this fact to prove an important non-local collapsing theorem. Now let me write down some corollary. That is the no-local collapsing theorem. So a little history. As a no-local collapsing theorem was originally proved by Theorem in order to exclude the cigar singularity in the analysis of three-dimensional Ricci flow. Because he has already proved the monotonicity formula for mu, he can show that for any Asian solution from the blow-up sequence of a compact Ricci flow, the entropy is always bounded below. then by using the no local collapsing theorem, we can show that any such Asian solution must be Kappa non-collapsed. So that automatically excludes the GAF singularity. So this is also called the Kappa non-collapsing property. Kappa non-collapsing property. So first of all, let me recall what does it mean by we say a Riemannian manifold has a Kappa non-collapsing property. So for any Riemannian manifold and any metric 4, if the scalar curvature is bounded above by r to the -2 on this geodesic 4, then the volume for this geodesic 4 is bounded below by Kappa times r to the nth. So here we automatically assume that Kappa is positive. Otherwise, this would be trivial. Okay, so it means that as long as on some geodesic 4 the scalar curvature is bounded above, then we know that the volume is bounded below. So here, this property is called the Kappa non-collapsing property. Now, by using the theorem I just mentioned, then we can prove that Ricci shrinker, the Kappa non-collapsing property holds. That is, we show that there exists a constant Kappa, which depends only on the dimension n and the mu, such that any Ricci shrinker, MNGF has the Kappa non-collapsing property. Actually, we can describe the Kappa a little bit more precisely. So this can be chosen as a constant Cn times e to the mu. So that means as long as we can control the scalar curvature on some 4 on the Ricci shrinker, then we can estimate the lower bound of the volume for this 4. Here, I will not go into details for the proof of no local collapsing, because this follows almost identically with the proof in the compact Ricci flow. The main idea is we choose some appropriate cutoff function in the entropy mu g tau. Then we use the fact that the mu g tau is bounded below to control the volume lower bound for the given geodesic force. Now, let me mention another property which I promised at the beginning for this lecture. That is, now we can estimate the integral, we can estimate the volume lower bound for the unit ball around our base point P. So here we have the BP1 should be bounded below by some constant Cn times e to the mu. Now, here, this corollary directly follows from the low. That's because the scalar curvature on the unit ball around the base point P is always bounded above. So recall that scalar curvature is bounded by Cn and is for BP1. So we can use the no local collapsing to derive the volume lower bound for the BP1. Now, in summary, we have shown that the volume for the unit ball around our base point is uniformly comparable to the e to the mu. So the comparison constant only depends on the dimension n. In other words, if the entropy mu goes to negative infinity, that means the volume for the BP1 is collapsing and vice versa. So that means the mu can be used as the scaling to measure how collapsed our Ricci shrinker is. Now, for the end of today's lecture, I will mention some other results for the global volume lower bound around the base point P. Here I will write down this as the third corollary. That is, we can show that let MNGF P be a Ricci shrinker. So here P as before is a minimal point for our potential function F. So if the scalar curvature is bounded by the constant C uniformly. So if that is uniformly bounded, then one can show that the BPR, that is the geodesic ball around P with the radius R, has the lower bound for the volume C times e to the mu times R. So here, this is true for any R is greater than or equal to 1. Here, the last constant C should be positive, and that means the volume for the geodesic ball around P increases at least linearly. One can compare this theorem with the classical theorem of Yao on the Riemannian manifold with non-negative Ricci curvature. So basically, this is the same result. Now I'll only sketch the proof. So this is just a covering argument. Now assume that we have a Ricci shrinker with the base point P, then we construct a geodesic ray from P. Then we can cover this geodesic ray with disjoint unit ball. So basically, if this geodesic ray is denoted by gamma, then we define Pi to be gamma 2i. Here is P1, then P2, and so on. Okay, now we can show that all those geodesic balls with the radius 1 are disjoint. And by the no-local collapsing theorem, we know that all BPI1 is bounded below by C0. So this is uniformly bounded below because the scalar curvature is uniformly bounded above. Then we can just combine all those volumes of all those geodesic balls to conclude that the volume for BPR should be bounded below by C0 times the constant the constant R. Now, with a little bit more careful analysis, you can see this C0 also depends on e to the mu. So here I will not go into details. Now I just want to mention that it was proved by myself and Wang that this is true. So the result is true for any Ricci shrinkers. It's true for any Ricci shrinkers. That means we do not need to impose the assumption that the scalar curvature is uniformly bounded. Actually, we'll use like more complicated techniques to achieve this, but I will not go into details for this. In sum, we show that for any non-compact Ricci shrinker, the volume increases at least linearly. Okay, this is today's lecture. And for the next lecture, I will talk about the weak-compactness theorem based on the estimate and the pyramid's entropy and some other stuff we derived in the first 3 lectures.